So again, we will walk through this as best as possible, and then we will answer questions as we get to them. So here we got table. All right. R1 bromo 2 methyl pentane can undergo either SN2 or E2 reaction with OH minus. Is this substrate primary, secondary, or tertiary alkyl halide? Give the product of each reaction. So answering the first question, is this a primary, secondary, or tertiary?
Primary.
For those of you at home that aren't live, you just take a look at, you find your halogen and look at the carbon that it's connected to and see if it's, see if there are, how many carbons that's attached to it. It's attached to this one, so it's only one, so it's going to be primary. So the question says that it can undergo SN2 and E2. So if you guys want, I will give you a 15-second head start if you want to work on the products for these two reactions, and then we will go through them. So for our SN2 reaction, we are simply going to substitute this bromine. This is not a stereocenter, so it should look just the same. So now it's going to have an OH. Remember, when we do these types of reactions, if you do have a stereocenter, it inverts. And this technically still does invert, but since it's not a stereocenter, it doesn't make a difference. Now for our elimination, this is our beta elimination. So if this is our alpha carbon that has the bromine, this is our beta. So we are going to remove a proton here. So now what this will look like, try to draw that again, is that this is simply going to take this, form a double bond and kick that off. So then we are going to have this. Is that what you guys got for that problem? Yes or no? Yay or nay? Which one did you make a mistake on?
The second one. So I had the same thing, just a double bond. I just didn't realize that the bromine it leaves, and so I would lose that like bond. But I still put it. And then I put the like wedge on top instead of the
straight line.
Yeah.
Yeah. So don't forget sp2 carbons, which is what you form right when you form a double bond. This is an sp2 carbon. As I try to draw that again, right there. That's an sp2 carbon. sp2 carbons don't have geometry. They're trigonoplanar, right? They don't have 3D geometry. It's a flat molecule. So if it was a stereocenter before, if that carbon's part of the elimination cycle, you just lose its stereochemistry. It just becomes flat.
And for the SN2 one, doesn't it just doesn't SN1 invert every time?
No, so SN2 inverts every time. Like this technically did invert, but is it a stereocenter?
No.
No, so it doesn't matter how I draw it.
So SN1 doesn't invert?
S1 keeps half of it the same and inverts the other half. Remember, SN1 gives you 50-50.
Right.
SN2 always inverts. But if it's not a stereocenter, you don't have to worry about it because it doesn't matter.
Okay.
Questions? Okay. All right. Just 1 second. Need to check something. Okay. So let's scroll down to our next problem. Sorry about that. It says C, when the reaction is cooled, the major product has an IHD of 0. What does IHD stand for you guys?
Honestly, no clue. I don't think I've ever seen a problem like this before.
Okay, I'm just going to double check because sometimes people just have slightly unique abbreviations, and I just want to make sure. So, okay, so I think it's degrees of unsaturation. Oh, hydrogen index of hydrogen deficiency. So, IHD is the same thing as degrees of unsaturation. That's a term that I have not heard in a long time. Just FYI, in case you're like, boy, I haven't heard that. Okay, so when the reaction is cooled, the major product has a degree of unsaturation of 0 and gives the following IR spectrum. Which of the products in B forms? Did we form the SN2 or the E2?
The SN2.
Yep. Why do you say that?
Because it has 0 degrees of saturation, and the pi bond wouldn't give it like 1 degree of saturation.
Mm-hmm. Yep. So if you formed a double bond, you would have a degree of unsaturation of 1, right? Your SN2 doesn't have any double bonds, so that's the key indication. Also, in your IR, what's this right here?
OH.
It's a big OH peak, right? And you only had that OH in your SN2 one. So there's two things here that you can kind of fall back on to say that this is the SN2 product. Does that make sense? Any questions? All right. And remember, this follows our trend, like we said. If you remember, we said OH minus, OMe minus, and OET minus are the only ones that can go SN2 or E2. And if you have a primary, SN2 is usually favored. But in this problem, just something to keep in mind. All right, let's go to our next one, 2. The following E2 reaction can form 3 different alkenes that are constitutional isomers. What's a constitutional isomer first?
Different connectivity.
Mm-hmm. Same chemical formula, just different connectivity. All right, so draw all 3 constitutional isomers and rank them from most stable to least stable. I'll give you guys 30-second head start, and then I'll start filling them in. I was really tempted not to get up and do anything tonight. Okay, so I will draw the first product that I came up with. Helps if I turn on the drawing tool. So what I can do right off the bat is that I know that when I do eliminations, when I do E2, I don't have rearrangements. I only have rearrangements in E1. So I can draw the skeletal structure for all of them. Actually, this last one's going to be a little bit different. So for my first one, I can have the double bond here, or I can have the double bond here. Those are probably the 2 easiest ones for you to see. However, there is one more product here, like this. Double bond's still there, but now this bond is going up.
Is number 3 just flipped?
Uh-huh.
Oh, okay.
Because remember, when you make a double bond, you can make a cis or a trans. So my most stable one is going to be this one. This is a trans double bond. Because here I have a hydrogen, right? So my biggest one on the left side is the CH3. The biggest one on the right side is the ethyl. They are going in opposite directions. So this is a trans double bond, or E. So this is good, right? Number 2 is going to be this one because it's the preferred double bond, right? Because it's between a tertiary and a secondary. So that's why this is why this one and this one are going to be your preferred. But this is preferred because this is trans double bond over this one, which is cis. Trans is always preferred over cis. And then this one is third because you did it to the outside, not the inside. Remember, you want to form your double bonds between the most substituted carbons. So here it's between a primary and a secondary, whereas here it's between a secondary and a tertiary, just like it's here between a secondary and a tertiary. Questions on that? How'd you guys do in that one? Okay. We're going to meet again tomorrow on Thursday, so we'll have time to go over stuff. All right. All right, so let's go ahead and go down to our next problem. Okay, predict the major organic product for the following SN1 reactions. Show stereochemistry when appropriate, i.e. draw both R and S products. If rearrangement or ring opening can occur, show the rearranged product. So I will give you guys I'll give you guys I'll give you a minute head start this time. I'll let you work on it. I'm gonna pause recording so that this doesn't keep going. Oh, sorry, I forgot I hit pause recording. So for this problem, for those of you just coming in, when I'm doing these problems, I check to see if they're stereocenters first, and the answer is no. So I don't have to worry about drawing both products because they're going to give me essentially the same thing. Next thing I look is that, are they tertiary? Yep, this is tertiary, this is tertiary. When I have a tertiary carbon, I don't have to worry about rearrangements happening. So essentially all I'm going to get then is this, right? And then I'm going to get this. So I don't have to worry about there being two versions of it, right? If they were stereocenters, I would have two answers. If I had a secondary carbon, then I would have to worry about a rearrangement. Does that make sense? All right. How'd you guys do on that one? I saw some head shaking as I was explaining stuff, so I saw maybe some small errors.
I treated them as if they were like steric, so I had like the enantiomers. So yeah.
Yeah, that's something you always have to watch out for. Also, everyone on this email, did you guys get my practice SN1, SN2, E1, E2 problems and all of the little sheets of information? Okay. I think I might have one more packet of stuff if you guys want some more stuff to work through. And I can dig through. All right. So again, let's take a look at these next two. I'll give you guys just 30 seconds this time to work on these two. Again, helps if I turn on my, so work on these two and see what you guys get. These are still the SN1 products. Let's go and go here. So the first thing, what's the first thing you think you should do for our next one before you even attempt to do it?
Draw it.
Draw it out. Yep. Because if you don't draw it out, you are just going to be giving, you're going to be putting yourself into a world of hurt. So pentane, 2-chloral, 2-methyl, right? Is this a stereocenter? It is not. As I die here, because you have a methyl and a methyl coming off. What is a key indicator also that it's not a stereocenter? They didn't tell you it was, right? They would have, if they give you the name, in the name, if they told you like R or S, then that was a dead giveaway. But in this one, they even tell you there's no stereocenter because it's not in the name. So because this is a tertiary, right? It is not a stereocenter. we are just simply going to replace our chlorine with our iodide. So that's all we should do. As Mags is being stalked by someone. Mags, look out. There's a stranger behind you. Okay. So again, it doesn't matter how you draw it. Essentially, you're just replacing that chlorine with an iodine. All right. So let's go ahead and go to the next one. So is this a stereocenter as drawn? Or do we have to worry about something else first? It's a secondary. So because it's a secondary, we're going to have what? Rearrangement. So a secondary next to a tertiary, right? What type of rearrangement do we have? Do we have a hydride shift or a methyl shift?
Is that a hydride shift?
Yep. We have a hydride shift. When it's a secondary next to a tertiary, we have a hydride shift. So our friend here, Mr. Hydride, which is the hydrogen with the bond, once this leaves, this is going to pop over. So our intermediate that we are going to form before our substitution occurs is that now this, we are going to have our methyl like this, and this is going to be a carbocation like that. So now, when this comes in and attacks, it's not a stereocenter anymore. So you're only going to have one product. When you had the hydride shift, it lost its stereospecificity. So now the product is simply going to be your benzene ring, not benzene, your cyclohexane ring with the methyl, and then with your O carboxylate, acetylate, acetylate, acetate. There you go, acetate group. That's what that is. I know my stuff, I promise. So you just simply add the acetate group. Questions on that one? Anger on that one? Melissa, why are you angry?
I don't know. I just feel like I need to review these more than I thought that I had to. So yeah.
That's okay.
I always mess up just like on the stereocenters. I'm like, oh yeah, there's no rearrangement with the stereocenter, but then it's not a stereocenter. So yeah.
Right. So let us try our next one. Give you guys just 30 seconds here this time. Okay, so is it a stereocenter? Yes, this time it is a stereocenter. So we're going to have two products now. Also, what type of carbon is it? It is a tertiary, it's a benzylic tertiary. If you have a carbon next to a benzene ring, that's extremely stable when it comes to S and 1 reactions because you form that, it's going to have resonance. If it's a tertiary benzylic, this is the most stable carbocation that you can form besides adding another benzene ring next to it. But this is literally as stable as this gets when you add resonance to it. So now, I'm not going to have a rearrangement, but you are going to get two products. So you're going to have one product where you keep the original stereospecificity, except now you're just going to add SH. And then you're going to have a second product where you are now going to flip that stereo center. So remember, this is just the way that you get it with SN1 is that you're going to get both stereo centers. So the easiest way to draw it is just flip which one has the dash, which one has the wedge.
Can you show the carbons that it's attached to? Because I only like see 2, but I'm not seeing the third one.
That carbon right there? Oh, the tertiary carbons?
Like the tertiary, yeah. I only see like the secondary carbon. I don't.
Well, 1 second. Okay. Did you see them?
Oh, I see.
Which one did you miss?
The wedge.
Yeah, don't forget that that's a metal. I would say of all of the times that students forget when you have a carbon, it's usually those like types of CH3s that are just sticking off on a wedge or a dash. They're easy to miss. All right. Any other questions on this one? Okay.
Oh, I have kind of like a silly question.
Mhm.
Because the way that I initially wrote it, I just kind of kept the first one like exactly how it was.
Mhm.
And I just like switched them. Like I didn't.
That's fine as long as one's on a wedge. They switch being on a dash and a wedge. It doesn't matter how you approach that.
Okay, that makes sense. Thank you. I just wanted to like clarify.
Mm-hmm. All right. Show the major organic products for the following SN2 reactions. Show stereochemistry when appropriate. So SN2 reactions, what happens if you have a stereo center? Do you retain, do you flip, or do you get both? You invert every time. If you have a stereo center, it is going to invert. So I will scroll down and I'm going to give you guys I'll give you guys a minute on these three and see what you get.
I'm finally done making my flashcards for the reactions.
Yeah.
It only took me like 2 days.
Hold on to them. They will be useful because you're going to have to do synthesis problems in second semester. Okay. So the first thing you should do in these ones too is also just ask yourself, are they stereo centers? So I'm simply going to come in and circle my carbon and say, all right, so this is the carbons where the chemistry is going to happen every time. All right. So stereo center, yes. Stereo center, no. Stereo center, no. So I don't have to worry about stereochemistry for the last two. I have to worry about it for the first one. So for my first one, whenever you get a, and I apologize for those of you having to listen to me chew my food. I really do apologize if you can hear it. But you simply, since it's on a dash, now it is going to be on a wedge. Any other stereo centers that are in my molecule will always stay the same. They are not impacted by my stereochemistry. Only the stereo center that's the site of my stereochemistry is going to have the reaction happen. For my second one, we have this, and all that's going to happen is that I'm simply going to replace that. Again, I don't have to worry about stereochemistry because that's not a stereo center. And then my last one is going to be the same thing, just like that. How did you guys do on that one? Better? Questions?
So for the first one, you would have two, right? It would be that one and then the one on a dash.
Nope, because remember SN2 only gives you one product.
Oh, I thought it was SN1 for a reason.
Nope, these are
For some
SN2.
reason. Okay.
1 second again.